All right, welcome back. So in this lecture we're going to talk about something called propositional equivalence, and this is also sometimes called logical equivalence. And as usual, we're going to continue to treat things like P, Q, R, S as being propositions. They're symbols that represent a declarative statement that has a truth value, a proposition. And it turns out that sometimes two propositions, even though they may be different from each other, are logically equivalent, meaning they always have the same truth value. For example, and this may not be true, but imagine it is, P could be the proposition it's raining, Q could be the proposition the ground is wet. And it may be that P and Q always have the same truth value. If it's raining, the ground is wet. And if it's not raining, the ground is not wet. And so when two propositions have the same truth value in all cases, we can write P is equivalent to Q, and it's this equal sign with 3 bars. And P is equivalent to Q is the same thing as P if and only if Q. This expression is saying if P is true, then Q is true, and if Q is true, P is true. So P and Q have to be true together, or they have to be false together. And that's just saying that they're logically equivalent. They have the same truth value in all cases. Now, there's some cases where, for example, P or not P is logically equivalent to true. And you can write the truth tables for P and for not P and for their or and see that in all cases this expression is true. This proposition, P or not P, is logically equivalent to true. Meaning that in any case, no matter what the value of P is, this expression has the truth value true. And an expression, a proposition that is always true, is called a tautology. So a tautology is a proposition that is logically equivalent to true. Now here's another proposition, P and not P. And this is saying that for this proposition to be true, P has to be true and not P has to be true. In other words, P must be true and false. And that never happens. So this proposition is logically equivalent to false. And a proposition that's equivalent to false is called a contradiction. But a proposition like P and Q is probably not in general equivalent to true or false. This is called a contingency. The value of this proposition depends on the values of P and Q. So it's neither a tautology nor a contradiction. Now we can work with logical equivalence by using our truth tables. So for example, here's something that I'm going to claim. The proposition if P then Q is logically equivalent to the proposition not P or Q. And how do we know that this is true? Well, let's make a truth table. And we'll list all the possibilities for P and Q. And we'll write down what we saw previously, the truth table for this conditional statement. And this fails to be true only when P is true and Q is false. In all other cases, if P then Q is true. Well, let's write down a truth table for not P, and that's just the complement of P. And now we can write a truth table for not P or Q, and this will be true if either this column or this column is true. So this is true, this is true, this is false, and this is true. And now in all cases, for any values of P and Q being true or false, we see that if P then Q has exactly the same truth value as not P or Q, that's enough to say these two expressions are logically equivalent, so this is a valid thing that we've written. And usually we can show equivalence by simply writing a truth table, but sometimes our expressions are very long and complex. If we had 8 terms that we were dealing with, our truth table would have 256 rows. And for a computer that might be fine, but for you and I, that's not a very efficient way to try to show logical equivalence. So this is where the role of identities come in. And identities are things like the following. P and true is equivalent to P. P or false is equivalent to P. P or P is equivalent to P, which is equivalent to P and P, and so on. So there's all these identities, these things that we know are true regardless of the value of P. And in your textbook, if you look on page 58, there's a list of all of these basic logical laws. These are basically identities, logical equivalences. For example, down here is the proposition that P ORed with, they use 0 for false, P ORed with false is equal to P, logically equivalent. So they're using a double arrow symbol to mean logically equivalent, and that's another way to write this equivalence. So we have all of these identities, and most of these are pretty familiar to us. Commutivity, P or Q is the same as Q or P. We can change the order. Associativeness, we can change the parentheses when we're taking an or an and of 3 expressions. Distribution, just like when we distribute a multiplication over a plus, we can distribute and over ors, and so on. And a few of these are familiar to us from 250, for example. De Morgan's law says the negation of P or Q is the same as the conjunction of not P with not Q. And there's a dual version of that. So you should look at these laws, and we'll play with these in class. But we can use these identities to prove other logical equivalences. So for example, let's say show that the negation of P or not P and Q is logically equivalent to not P and not Q. Okay, how do we show logical equivalence? We could do a truth table, but I don't want to do a truth table. I want to do this using some of these identities that are given to us in the book. So let's start off with the left side, the negation of P or not P and Q. And let's find what that's equivalent to. Well, we have a De Morgan's theorem, which says negation of A or B is equivalent to negation of A and negation of B. Well, here's a negation. A is this first thing, B is this thing. So I'm just going to apply De Morgan's theorem and say this is equivalent to not P ANDed with the negation of that second term. And my reason for that is going to be De Morgan's theorem. So I would write that out on a test, but DMT for De Morgan's theorem. And then this is equivalent to, well, I'm going to leave the not P, and I'm going to apply De Morgan's theorem on this piece and say the negation of something and something is the negation of the first ORed with the negation of the second. And that's De Morgan's theorem again. And now I'm going to say that this is equivalent to not P and there's an identity down here at the bottom called the involution law, which says not P is equivalent to P. So I can take this not P and replace that with P, and that's involution. And now I'm going to do a distribution. So our distribution law says that if we have P ANDed with Q or R, we can distribute that P with the Q and the R and OR those two resulting expressions. So you got to be careful. You got to just kind of do this as kind of a blind operation. So not P ANDed with this would be not P ANDed with P, ORed with not P ANDed with not Q. Right? So I took this and put it with P, and then I took this and put it with not Q, and I just ORed those together. So that's distribution. And not P ANDed with P, we have an identity about that, right? Not P ANDed with P. Well, we have P ANDed with not P is equivalent to false. So before we can actually use this, we have to write this not P ANDed with P as follows: P ANDed with not P, or, and we'll leave the second term the same. And that's commutivity. Right? And now we have P ANDed with not P, and we have an identity which says P ANDed with not P is equivalent to false. So this is equivalent to false, or not P ANDed with not Q. And what was that identity called? That's called negation. And we got one more place to go, which is false ORed with something is equivalent to the original something. But again, we should probably use commutativity one more time and change this to make it look like the actual identity. So I'm going to use commutativity once more and say that this is equivalent to not P and not Q, ORed with false. That's commutativity. And now I'm going to take this identity which says something ORed with false is equivalent to something P ORed with false is equivalent to false is equivalent to P. So this thing ORed with false is equivalent to not P and not Q. And that is the identity law. And so we have shown that this expression here on the left is logically equivalent to not P and not Q, which is what we were asked to show. And so at this point we can say QED, which is Latin for which was what we were asked to demonstrate. And so we have just proven that this expression is logically equivalent to this, and we did it by applying a series of identities. So we'll have some practice with this in class also, but that's basically the gist of how all of our proofs are going to lay out. And it doesn't always end up being this complicated. We can start taking some shortcuts, but for the first few times that we do this, we want to be this rigorous. We want to make sure that if we're using the identity rule, that it actually matches the identity rule. So if it's false or something, we're going to apply commutativity to make it something or false to match the actual statement of that identity law. All right, so we're going to go on and talk about predicates and quantifiers next.